Okay, everybody, I'm going to address a question that has come up actually a few times, and I've talked to people kind of individually about it. Now I'm going to put together a little video for it. I want to talk about the relationship between radicals and exponents. Okay, and going back and forth between them. Between the two of them here, we want to talk very specifically about how that works. Okay, now actually, sorry, it's rotated a little bit here. Now, to do this, we're going to come at this from two different directions here. So first of all, I'm going to talk about radicals here. I'm going to talk about where this idea comes from. So this goes back to the idea of a square here and finding the area of a square. Okay, in order for me to get the area of a square, what I do is I take the length of this side, the length of this side, and then I multiply them together to get the area of the square. Now, because it's a square, all sides are equal. And so the two factors here, the length and the width, are both the same number here. And so that's what that symbol means up there when I have to the power of, or the exponent of 2. Okay, that means that what I've actually got here is x is showing up as a factor twice. It's x multiplied by itself, and we know that. Okay, you totally know that. So if you've got a square here, okay, and let's say that the side length here is 4, the side length is 4, we know that the area is 16. Okay, 4 times 4 is 16. And that's what that means. In fact, that's why we call it squared, x squared, because we're forming, okay, a square out of it. And we're getting the area of the corresponding square. Okay, with that in mind, we're going to take this a little further, because what happens when you know the area and you want to know what the sides are? Okay, so now I know what the area is, and I'm actually interested in what these sides are to produce this square. Well, to do that, we use this symbol. So if we're going to call this, let's say x I don't know, x is I don't know, then what we do is we introduce this symbol right here. And so what that symbol does is it takes us from the area of the square. And it's important that you understand that this is a square. And it gives us the length of the sides, each side being identical. Okay? So each side length here is going to be the square root of a. Now, what that means, okay, is that the square root of a multiplied by the square root of a is going to be a. The side length of the square multiplied by itself should get me the area of the square. That's what that means. That's where this comes from. In fact, this is why we call it a square root. I'm trying to build the dimensions now of the square. So, for example, let's go backwards and let's just say that we've got a square here. Let's got an area of 9. Okay, that's an easy one to work with. If I want to determine what the side lengths are that produced that square, okay, actually, you know what? I'm going to use a different number here, actually, because it just occurred to me that there might be a different way to talk about this just for clarity's sake here. Let's talk about 16 again. Okay, if I want to figure out what the side lengths are, this is going to be the square root of 16. This would be the square root of 16. Okay, now these two numbers are going to be identical to each other because I'm producing a square. So I know that the root of 16 multiplied by the root of 16 must equal the area of this square, 16. Now, in this particular case here, we know what those numbers are. Okay, we know that that's got to be 4. And that's got to be 4. It's because that's an easy thing to get my head wrapped around. I know what the side length's got to be here. Now, it can't be 2 and 8. Now, 2 times 8 also gets me 16. But that would produce a rectangle, right? 2 by 8. And that's not what I'm asking for. I'm asking for what would the dimensions of a square be? Well, there's only one number here that I can put on this side, and that gets me 16. And that's got to be 4 and 4. It's not a rectangle. It has to obey this rule because we're talking about a square. So, what that means, okay, is that if I've got, for example, the square root of 9, and I multiply that by the square root of 9, what this is saying is, what would the side length have to be to get an area of 9? And if I multiply that by itself, this has got to be equal to 9. It's got to produce a square with an area of 9. So this symbol says going backwards from the area to the side. Going backwards from the area to the side multiplying those together is getting me the area. So if I've got the square root of 25, square root of 25, what this is saying is I know that I've got a square with an area of 25. What's the side length? And if I multiply that by itself, that's the other side, together, that is going to get me the area of that square, 25. Now, in these two cases here, I know what those side lengths are. That's going to be 3 multiplied by 3. In this case, I know that's going to be 5 multiplied by 5. But this relationship still holds even if I'm unaware of that. So for example, what if I've got a square that's got an area of 7? Well, then the side length is going to be root 7. Multiplied by root 7 will get me 7, because this is the side length of an area, the side length of a square with an area of 7. If I multiply that by itself, there's my length, there's my width, put them together, I'm going to get a square that's got an area of 7. Now, I don't know what those numbers are. I know that they exist because I know that I can get a square with an area of 7. And that's not that hard. But what are those exact sides? Well, I don't know. And so that is actually the best that I can tell you. I can't give you the specific decimal numbers. And in fact, I suspect those numbers go off forever. I believe they're irrational numbers there. Those decimals are going to go on forever. I couldn't write them completely. The best I can do is to write that as root 7 multiplied by root 7, and that's what's going to get me 7. Okay? So you need to understand how that works there. Now, let's come at this from a slightly different direction. Let's talk about this now in terms of exponents. Okay? You know that if you multiply two powers together, a to the m multiplied by a to the n, that when you do that, that is the same as taking that base a to the power of, to the exponent of m plus n. That's just a law of algebra. Okay, we know that that works. Now, this is a little bit easier to get to the point that I want to get to here. Okay, we know that that works. So, we know that if I've got, for example, 3 to the 4 multiplied by 3 to the 5, that is going to be the same as 3 to the 9. I'm totally okay with that. I know that if I've got, for example, 3 to the 2 multiplied by 3 to the negative 4, again, I can just add those exponents and I'll get 3 to the negative 2. Even if it's negative, I have no problems with it. I continue to just add them together. And that's great. Okay, so now I'm going to get to the real issue here, and we're going to pull these two together now. So I know that, for example, if I've got the square root of 3 and I multiply that by the square root of 3, I know that what that means is I've got a square with an area of 3. This is the length of its side. That is, again, the length of its side. And when I multiply those two together, I will produce the area of that square, which must be 3. Okay, because when I use this notation, I'm starting with the assumption that I got a square there with an area of 3. So root 3 times root 3 is 3. Now, just kind of picking this up here, I know that when I multiply powers together with their bases are the same, I add the exponents. So I notice something here rather interesting, that if I multiply two powers of 3 together, let's just say in this instance that I've got 3 to the 1/2 multiplied by 3 to the 1/2. Now, I'm choosing these. Okay, I'm choosing these very, very specifically because I know that when I multiply those together, I add the exponents, and I know that 1/2 plus 1/2 is equal to 1. Okay, so this is not an arbitrary decision, but I'm kind of zeroing in on these exponents because I already know that when I put those together, I'm going to get a 1, just like up here. So now let's just take a quick look at what's going on here. I've got this thing multiplied by itself equals 3 to the 1. I've got this factor here multiplied by itself is equal to 3 to the 1. So what I've basically just said here is that when I take the square root of 3 and square it, I'm getting 3 to the power of 1. If I take 3 to the 1/2 and square it, multiply it by itself, I get 3 to the power of 1. Okay, well, it shouldn't take much to realize that, hey, those two pieces there, the base here squared, getting me the exact same thing, those must be equivalent. So we can conclude that the square root of 3 is equal to 3 to the 1/2. It has to be that way for our notation and whatnot here to be consistent. Okay, that has to be true. Now I know this has been a little bit of a long-winded explanation of this. I could have really just jumped to this here. But I found that a lot of people really don't understand radical notation. Like they do not realize right off the top there, or it's not immediately obvious to them that root 3 multiplied by root 3 is actually just equal to 3. Okay, root 10 multiplied by root 10 is equal to 10. Usually that needs a little bit of explanation to get to this point where people are comfortable with what's going on here. This is usually a lot more straightforward. I know that I just add the exponents together. That rule has been established well early on. Okay, but because these two are true and they both equal the same thing, and all I'm doing is squaring one factor in both cases, those two factors must be the same. And that's why that relationship is true.